Converging lenses. A thin lens is a lens whose thickness is small compared to its radius of curvature. Lenses can be converging or diverging. Converging lenses are thicker in the center than at the edges. Diverging lenses are thicker at the edges than in the center. Converging lenses bring parallel rays to a focus, which is the focal point. Diverging lenses make parallel light diverge. The focal point is the point where the rays would converge if the rays were projected backwards from the lens. The principal axis passes through the center of the lens. The optical center is where rays go straight through the lens without bending. The focal point is where parallel rays meet at a common point and are in focus. The focal length is the distance between the focal point and the optical center. Diverging lenses are thicker at the edges than in the center. Diverging lenses make parallel light rays diverge. The focal point is the point where the rays would converge if the rays were projected back. Analysis of diverging lenses will not be a part of this unit. For plane mirrors, images are always virtual, and they are always behind the mirror. This is because image formation in a plane mirror is based on light reflection. For lenses, images are real if they are on the opposite side of the lens from the object. They are virtual if they're on the same side. This is because image formation is based on light refraction. Unlike mirrors, lens images are real if they're on the opposite side of the lens from the object. The images are virtual if they're on the same side as the object. So, virtual images are formed on this side of the lens. So if this is the object, and here's the lens, this is where the virtual images would be, where real images would be formed on this side of the lens. Ray tracing can be used to find the location and size of the image created by thin lenses as well as mirrors. These are the steps for converging lenses. For the purpose of ray tracing, label a focal point on both sides of the lenses. Number 1. The first ray enters parallel to the principal axis and exits through the focal point on the other side of the lens. The next ray enters through the focal point on the same side of the lens and exits parallel to the principal axis. The last ray goes through the center of the lens and is not refracted. The image created by a converging lens will be examined for 3 different object positions: beyond twice the focal length, between the focal length and 2 times the focal length, and between the lens and the focal length. An object, typically represented by an arrow, is placed outside the 2F position. Then we're going to draw 3 rays to find the image. The first ray enters parallel to the axis and exits through the focal point on the other side. The second ray enters through the focal point on the same side of the object and exits parallel to the axis. The third ray goes right through the center of the lens, known as the optical center, and it is not refracted, which means it doesn't bend at all, it just goes straight through. The image is represented by a dashed black arrow. The image is demagnified, real, and inverted. A demagnified image is smaller than the original object. A real image is on the other side of the lens from the object, and inverted means the image is upside down on the other side of the lens. The arrows indicating the object and the image are copied out of the ray diagram and pasted here to illustrate what it means to be demagnified. Compare the size of the 2 arrows. The image of the object is smaller than the actual object, so it is demagnified. The arrows indicating the object and the image are copied out of the ray diagram to illustrate what it means to be a real image. Compare the location of the 2 arrows. The image of the object is to the right of the lens, therefore it is a real image. The arrows indicating the object and the image are copied out of the ray diagram and pasted here to illustrate what it means to be an inverted image. The image of the object is upside down. You can see the image arrow is pointed down because all of these rays came from the very top of the arrow, so therefore the rays will all intersect at the top of the arrow. In the base of the arrow, rays coming off of here are just going to go straight through, and they're going to be on the principal axis on the other side. So therefore, compared to the actual object, the image will be upside down. It will be inverted. This time, we're moving the object forward to be between the focal length and 2 times the focal length. So we still start by drawing one ray parallel to the axis and having it exit through the focal point on the other side. The second ray goes through the focal point on the same side as the object and then exits parallel to the axis. The third ray goes through the center of the lens and is not refracted. It's not deflected, it doesn't bend at all. We only need 2 rays to see where the image is located, but 3 or more rays will confirm the location. The image here is magnified, real, and inverted. A magnified image is bigger than the original object. If we go ahead and move that object even closer, we're now between the lens and the focal point. The first ray goes parallel to the axis and then exits through the focal point on the other side. The second ray enters through the focal point on the same side and exits parallel to the axis. So actually we're kind of drawing the line from over here through the focal point, touching the tip of the object all the way up to the lens, and then parallel. The third ray goes straight through the center of the lens and is not refracted. These rays don't intersect on the right side of the lens, so a real image is not formed. When that happens, we actually extend the lines backwards, shown as dashed lines, back behind the object, where they will converge over here, forming a virtual image. The image is magnified, virtual, and upright. A virtual image is on the same side of the lens as the object and is created by our eyes, tracing the light rays backwards to where they should originate from. An upright image is not upside down. Here is a summary chart showing all of the results from having the object at different positions. So you can see that if the object's very far away, more than twice the focal length, it will be smaller, otherwise it will be larger. If the object is inside of the focal point, it will be virtual and upright, otherwise it will be real and inverted. A candle is located 22 centimeters from a converging lens that has a focal length of 10 centimeters. Draw a ray diagram and describe the image formed in terms of real or virtual, location, and magnification. So as you can see right here, the image ends up being demagnified, real, and inverted.